this is Jason Kendall, and welcome to the next in my cosmology series. This is the fourth in chapter 2 of Barbara Ryden's cosmology textbook, Introduction to Cosmology. I'm going through the entire textbook, and if you are just tuning in for the first time, please see the link to the playlist in the description and go watch everything in advance first so that you can follow along in the correct order. That being said, let's begin with the different kinds of particles that exist in the universe. Okay, so let's begin by saying in cosmology, we want to look at all of the kinds of particles that matter cosmologically. And so this list is actually pretty short. We care about protons, we care about neutrons, we care about electrons, we care about neutrinos, we care about photons, and we care about dark matter. These are the dominant things that we care about in cosmology. And each of them, as you see in this little table, we have their symbols, where the proton is a P and neutrons an N, and electrons an E with a superscript minus. You have the neutrinos, which are the nu, the Greek letter nu, and they are three different flavors. There's the electron, nu, and tau. Photons are always given by gammas. And dark matter, we don't know what it is, so I'm just giving a crazy little icon there. Notice their rest energies and notice their charges. And so these are the typical particles that we're going to be talking about in this lecture. So when we do talk about particles, I'm ignoring a huge number of things that are in the standard model of elementary particle physics. Notice there are 17 different fundamental particles. There's 6 quarks, there's 6 leptons, there are 4 boson force carriers, and 1 scalar boson, the Higgs boson. All of these things are important for the standard model. However, many of them don't really matter to us in a certain regard. And I'm talking specifically about the quarks here, but all the rest of them do matter in other regards, as we'll talk about shortly. But these are our fundamental objects, and they're grouped into 2 different types of groups. One's the fermions and one's the bosons. Let's look more carefully at all these 17 particles in elementary particle physics. So we have 3 basic kinds of groups. There's fermions, hadrons, and bosons. Now, fermions have spin 1/2. It's one of their quantum numbers is a spin for all of these. And fermions all have 1/2 spin. Bosons all have single integer spin, or spin 1. Now, fermions can be broken into 2 different groups, leptons and baryons. And leptons are like the electrons and the neutrinos, and baryons are combinations or bundles of 3 quarks. Say 2 charms and a strange, or an antibottom, a bottom, and a top, or whatever, or 2 ups and a down. Those would be baryons. The other type of hadrons, which are quark bundles, are mesons, which would be a quark and its antiquark particularly. But all of the charges in a hadron must add up to 0 or 1. They have to be integers. We can't have anything in nature that is a non-integer, charge. So you notice how the charges on quarks are in units of 1/3. Either they're up at plus 2/3 or minus 1/3. And so you can add them together, like a top and an antitop makes a meson, and a top and a pair of bottoms makes a baryon. So those are our types of things. Now, leptons are fundamental particles, and quarks are fundamental particles. In fact, all of these are fundamental particles, meaning none of them can be broken down into smaller and smaller things. On the other side, mesons, because when there's 2 of them, they will have a unit spin, because the quarks all have 1/2 spin, and if you have 2 of them, you get a single integer spin. Now that makes them bosons, and so bosons all have integer spin. Now there's certain ones that don't have mass. Notice that bosons that are force carriers are over on the right-hand side. The gluon is the force carrier for the strong nuclear force. The photon is the force carrier for the electromagnetic force. And the Z and W bosons are the force carriers for the weak nuclear force. The Higgs particle is the thing that creates the field of mass that we have. So Well, notice that I didn't include anything else. I mean, there is possibility, there's nothing excluding four quark bundles or five quarks or pentaquarks, but these pentaquark exotic baryons don't seem to exist in the wild, and neither do exotic tetraquark mesons. They are not barred from the standard model of particle physics, and they have been made and observed in particle colliders, but they don't exist in free space. They decay extraordinarily rapidly, and then they're done. But remember, all of these things, the quarks must combine together to make integral charges, and those are the only kind of charges that are found in nature. So however you bunch the quarks together, that's how you get them. Now, quarks are so interesting. Let's talk a little bit more about them, about 2, 3, and 4, 5 quarks. So if they're in even numbers, they're called mesons, and if they're odd numbers, they'll be called baryons. If there are 2 or 3, they're normal meson or baryons, and anything greater than 3 will be exotics. And basically in quantum chromodynamics, this is how we actually know how quarks stay together. A quark's color can take one of three values of a color charge, red, green, and blue. And an antiquark can take one of the anti-colors, like anti-red, anti-green, or anti-blue. And they're represented by cyan and magenta and yellow in various and sundry diagrams. Gluons, which are the force carriers of the strong nuclear force, are mixtures of two colors, such as a red and an anti-green, which constitutes their color charge. So a baryon is composed of three quarks, in which each must have one of the colors red, green, and blue. Likewise, an antibaryon is composed of three antiquarks, one of which of each anti-red, anti-green, and anti-blue. And a meson is just simply made up of one quark and an antiquark, and therefore it has its color and its matching anticolor. All three of the colors, when mixed together, or any of these colors and its complement or negative, they're called colorless or white, and they have a net color charge of 0. And this is in a bound baryon, you'll find the color charge of the quarks as well as the two color charge of the gluon all add up to white. So let's say there's a green, red, and a blue. And then the gluon will say, I'm going to take my blue charge and leave a red. And so we now have an anti-red on the gluon and a blue. So the gluon now becomes blue and anti-red, shuffles over to the red charge, turns that red charge into a blue, leaving the red charge behind. And so the gluon will carry the source's color and the destination's anticolor as it traverses around. And so that's how quark gluon interactions go. Well, how does this relate to cosmology? Okay, so the only stable known baryons are the protons and the neutrons. And a proton is composed of two ups and a down quark, and a neutron is two downs and an up quark. Now, neutrons decay in about 15 minutes if they're free, and they won't fall apart if they're bound in a nucleus, say two neutrons and two protons in a helium nucleus. They won't decay. But if they're free and just roaming around, they're going to decay and break apart into a proton, an electron, and an antineutrino really quickly. But they're just also a little bit more massive than protons, and keeping things down, like a down quark, I guess, takes some weight, apparently. You'll notice that the mass of the neutron is about 939.6 megaelectron volts per c squared, where we usually say the c squared gives us a mass. So if we take the rest energy and divide it by the speed of light squared, we'll get a mass. But typically in particle physics, we quote things in megaelectron volts. That's typical for these things. Notice that the proton's rest mass is about 938.3 megaelectron volts per c squared. That's its rest mass. And it's a little bit less. Now, the neutron has zero charge because of the sum of the quarks, and the proton has a plus charge because of the sum of the quark charges. So now the proton, though, is one of the most stable objects known. Its half-life is at least 1.7 times 10 to the 34th years, at least. And this is according to recent studies and recent attempts to actually find it, specifically by the Kamiokande experiment in Japan. Now, that's a long time. That's 10 to the 24th Hubble times, or 10 to the 24th times the current age of the universe. Protons are pretty stable. Now, what about charm and strange and top and bottom? Well, they don't make stable baryons. They do not make them. So these are the most stable and baryons known. Now we go over to the leptons, and specifically the electron. The electron is our special friend from all the leptons. It makes, with a proton, and neutrons, makes up atomic nuclei. And they are tiny compared to the proton. They're approximately 1,840 times less massive. You'll see they're about a half a mega electron volt divided by c squared, of course. And they have a negative charge. And what's interesting is it looks like in the universe, there's one electron for every proton in existence. The universe appears to be electrically neutral, which is a fascinating, fascinating thought. Why should that be? Why is the exact number almost identical? Well, it's a good question. And I'll have to get around to that in a future video, I'm sure, because that's just too fascinating to let go. Anyway, moving right along, leptons are also part of the fermion group, and they're fundamental particles. There's also the muons and tau particles as well. And let's see what else we have. Next, we notice that 3/4 of all baryonic matter in the universe is hydrogen, with about 24% being helium, and there are various and sundry isotopes. But specifically, deuterium is very greatly depleted with respect to hydrogen, as is light helium. So it's pretty much just a proton with an electron spinning around it and a standard helium nucleus. That makes up almost all of the entire universe in terms of matter, in terms of baryonic matter. Basically, the universe is pretty basic. I mean, that's all there is to it. And so these are basically the particles of the universe: protons, neutrons, electrons, deuterium nuclei, light helium, a trace amount of tritium, which I didn't put in there, normal helium, and just a regular proton, a proton with an electron going around it, making up a hydrogen atom. This is it for the thing. Now, astronomers have an odd language, and this is their side note. Even though electrons are leptons, but since they come with 1-to-1 with protons, they're lumped into baryonic matter. Um, so when people say, oh, non-baryonic matter, they don't mean electrons. They do mean electrons for baryonic matter because they get dragged along for the electric neutrality. Now, they're 1,800 times less massive, so they barely contribute any serious mass to the universe, but they're not lumped in as non-baryonic matter for things that we'll talk about later. So if you're a particle physicist, please squirm now. I can't help you there. It's just the way it is. Electrons are lumped in with baryonic matter. Now let's look at another interesting side of the leptons. Neutrinos are another hugely populating particle throughout the cosmos. They're also leptons, and they basically don't interact with anything. They can pass through a parsec of lead without hitting a single nucleus. And we know about them principally through the nuclear reactions that are necessary to power the sun. And neutrinos can transform one into each other more easily in the presence of matter. Each flavor of neutrino, meaning electron neutrino, muon neutrino, or tau neutrino, is a quantum superposition of 3 different masses, which is kind of a weird way of saying things. That they can oscillate between each other is what's called the MSW effect. And go see my solar neutrino problem video to learn a lot more about this. So these things are really weird. And from the Planck cosmic microwave background results, we have an upper limit to their masses, because this is another thing. We don't know what their actual masses are. We know they exist, but we don't know what their masses are. We know the sum of their masses squared has to be less than 1/4 of an electron volt for all 3, and that's from the Planck 2018 cosmic microwave background results from the anisotropy, from understanding the power spectrum of the anisotropy. Now, the Hubble tension issue can raise that value of 0.26 electron volts up to a total mass of about 68 electron volts. And that depends on the data set that's used and the methodology of the appropriately weighted combinations of the compatible data sets, such as ACT Data Release 4, the WMAP, Baryon Acoustic Sky Survey, and the SHOES collaboration. Now, this is because the Planck data is in tension with respect to more direct measurements of the Hubble parameter. So the Hubble parameter today is called the Hubble constant, and the cosmic microwave background shows it to be one thing, and these other things show it to be something different. And as a result, that changes the upper limit of the sum of the masses squared, which is really interesting. With all this, we certainly do know that neutrinos actually exist. We know about them as a result of the proton-proton chain in the center of the sun. Also, when a neutron decays into a proton and an electron, a predicted byproduct is an anti-electron neutrino, which has been observed in particle colliders. So, neutrinos have been posited to exist for a long time and have been observed coming from the sun and also from supernova 1987A, the first detection of neutrinos from a dying star. Now, this is where it gets kind of weird. We're used to thinking of particles as having mass, such as protons and neutrons. We know we can measure their masses in kilograms. And neutrinos were, when they were first originally considered, were thought to be massless. But now we know they have some finite mass. But the neutrino mass states do not correspond uniquely to the different flavors of the neutrinos. Neutrinos have three separate mass states, each of which are fractional probabilistic combinations of the three flavors. So as you can see from this diagram, we have we have the three colors for the three different flavors. We have the electron, muon neutrino, and the tau neutrino, and they're red, yellow, and blue. And you can see that the probability that it's one of those things gives it that mass. So the probability distribution shows what that mass number should be. And so there's three different mass states that correspond to three different combinations of the probabilities of whether or not it is that flavor. That's crazy to think about. So there's two possibilities for these groups, and their mass hierarchies, we'll call them the normal one on the left and the inverted hierarchy on the right. And so there's state 1 is the lowest in the normal, state 2 is above that, and it has a difference of the sum of the squares of two of the mass states. And then from 2 to 3 is the difference of a different pair of mass states. Now, the separation between these mass states depends on how they're measured. The smaller difference, delta m sol, comes from the measurement of the oscillation of solar neutrinos. This mass difference was responsible for the solar neutrino problem, where the total number of electron neutrinos was 1/3 of what was expected. The larger mass difference arises from the neutrino oscillations occurring due to cosmic rays striking the Earth's upper atmosphere. Such collisions create muons, which then decay rapidly to muon neutrinos and electron antineutrinos. The mass difference between delta M ATM reflects this interaction. Both of these differences are between squares of the mass eigenstates. We know the differences of the squares of each of the two mass states, but we don't know the individual masses for each neutrino. Instead, each mass state is made up of a combination of three flavors, as you can see illustrated. We don't know the absolute masses M1, M2, or M3 of any of these eigenstates. We just don't know. So delta m sub sol squared is equal to the state 2 squared minus state 1 squared, and that's approximately 7.5 times 10 to the minus fifth electron volts squared. Of course, you can divide by a c to the fourth here to get mass squared, but the energies in particle physics are usually stated in rest mass energies. Next, the atmospheric oscillations show that the mass differences between states 3 and 2, and that's approximately 2.5 times 10 to the minus 3 electron volts squared. The difference between the normal and inverted hierarchy will change those numbers a little bit. So let's take a guess and have fun with particle physics. Assume that the hierarchy is normal. If you prowl around the literature, it seems like there's a consensus that it's probably the normal hierarchy, meaning the left-hand diagram. So let's use that. Let's also then pretend that the mass state 1 is exactly 0. Then mass state 2 would be 8.7 times 10 to the minus 3 electron volts per c squared, and that quickly gives a mass state 3 of 0.507 electron volts. That's all nice and everything, but there is no requirement that the first mass state is 0, though. It's just a helpful exercise. Actually getting this mass is an active area of research with the Karlsruhe tritium neutrino experiment. This has the wonderful acronym of CATRIN. This experiment is trying to directly measure electron neutrino mass. In 2022, they reported a direct measurement of the electron antineutrino as just a little bit less than 0.8 electron volts per c squared. So neutrinos are not massless, but it's still possible that one of the mass states is massless. Neutrinos are really interesting. Cosmologically, we expect the universe to be filled with neutrinos, not just produced by nuclear fusion in stars or from the relativistic collisions in the interstellar medium, but principally, we expect the vast majority to have been formed during the nucleosynthesis epoch of the Big Bang. Their number density should be extremely large, about a quarter of the number of cosmic microwave photons, which far exceed the total number of baryons in the universe. Okay, let's look at the next of our friends from the particle zoo that are cosmologically relevant, photons. Photons are very familiar to you. That's how you see things. And photons in our bucket that we're looking at, they have no mass. They are massless. They are spin one bosons, but they are electromagnetic radiation, and they have a particle-wave duality, and they can be thought of as either a wave or a stream of particles, depending on how you're measuring them. And both are measurable. So as a wave, it has a wavelength of lambda, which is equal to the speed of light divided by the frequency. And as a particle, photons have an energy and a momentum. But remember, even though they have momentum, they have no mass, where the energy of the photon, and we always use the subscript gamma for a photon, is equal to Planck's constant times the frequency, where h is equal to 2 pi times h bar, which is, of course, Planck's constant. But photons can come in a huge array of wavelengths spanning from gamma rays through visible light, through back up to X-rays, back down to UV, all the way down to infrared, to radio, and the deepest, longest radio wavelengths. So they interact very readily with anything with a charge. They do through photoexcitation, which is exciting electrons in atoms up to higher levels, photoionization, where the electrons are kicked out of atoms, and photodissociation, where a high energy gamma ray can break apart a nucleus. And there's lots of names for these interactions. Free-free interactions, bound-free interactions, bound-bound, Bremsstrahlung, Compton scattering. All of these things are ways that photons interact with charged particles. In general, the photon can impart or take away energy from electrically charged particles, and they can easily be created by charged particles moving in the presence of other charged particles, or accelerating in the presence of other charged particles, or simply vibrating. The best way to think about a photon is that it is a packet of waves, a wave packet traveling from here to there along an electromagnetic field line that is infinite in extent. To learn more about this, go look at my entire long video on atoms and light. Let's look at a very important element of the nature of photons, and one of the most common things we're going to be talking about, and it'll be very important cosmologically, is the black body spectrum. So let's start with the idea that if you have an object that is dense and hot, then the electrons and protons and neutrons will interact, and they'll bounce off each other and vibrate against each other, and will create photons with an energy distribution that will match the thermal properties of the matter. Basically, all these particles in the object or system will be characterized by a single temperature T, and that will include the photons too. The chemical or nuclear makeup of the object does not matter at all. It's only the temperature when it's a dense object that's been all raised to the same thermal properties. The energy density of the photons in such an environment, let's look at their frequencies in a small, tiny range of, say, F up through F plus dF, which dF is a little tiny range. And this is given by the blackbody function that you see here. So epsilon as a function of frequency, and epsilon here is going to be in units of energy per unit volume per frequency band. So that's what we're going to be looking at. So you can see that there's an h bar, 8 pi h bar over c squared, and then you've got this function f cubed df, which is that little tiny thing. So we're looking at a differential equation. And at the bottom are the statistics for boson statistics, which is the exp hf over kt minus 1. That's the statistics, the thermal statistics for bosons. This is an interesting function, and in fact, there's a self-similar shape that I want to show you in that graph that we're looking at. That's that one little curve. That's the black-body curve. Let's say now we redefine the variable x is equal to hf over kt, which is in the exponential. And we're going to reassign everything such that x is equal to hf over kt. And we get a new version of that formula. So you have e of x dx instead. And now you've got all the x's in the second part, which is x cubed dx over expx of minus 1. So that's our functional form of, say, x. But then the left-hand side is just a scale factor, which is 8 pi k cubed t cubed c cubed over c cubed h squared. And so that's a scale factor that would be applied to that curve. And so if you look closely, that curve that we see in the graph, that is simply the x cubed over but the exponential of x minus 1. And the t cubed is only it just will amplify everything on that curve the same. So all black-body curves are the same. They all have the same shape. They're just changed by the scale factor of that c cubed h squared over 8 pi k cubed t cubed, with t is the temperature of the distribution. Otherwise, they're always the same. Now, the peak of the spectrum is that approximately the energy of the peak is hf peak, which is approximately 2.82 times kT, where kT is the characteristic thermal energy content of a particle in the gas. K is, of course, the Boltzmann constant, and T is the temperature. That's the energy of the peak of the blackbody curve, and you can see that the hotter it is, the higher the energy. So first we have the energy density inside of a range. But what if we integrate the entire thing to get the energy density of the entire blackbody photon field? So that's epsilon sub gamma, and that's equal to 4 over c times sigma, the Stefan-Boltzmann constant, times the temperature to the fourth power. That 4 over c arises from how the direction of diffusion and rate of movement of photons inside of a field are measured and integrated. 4 sigma over c is the radiation constant, which is that big squirrely nest of constants you see there. But notice the units. It's 7.56 times 10 to the minus 16th joules per cubic meter per Kelvin to the fourth. So this is an energy density. And the energy density depends on a constant times the temperature to the fourth power. So if you have twice as hot a gas of photons, it will have 16 times the energy density. So because the energy of a photon is h times the frequency, we can say what's the total number density of photons inside of the field. So we just take the energy density and divide it by the energy of one photon, and we have the number density of photons in a small frequency interval df. It's very similar to the previous expression, but there's an f squared instead of an f cubed. This will end up, after integration, to give a total number density of photons that depends on the temperature cubed. And if you work out the value of that beta constant, that constant beta, it's about 2 times 10 to the 7th photons per cubic meter per degree of temperature cubed. So there's a lot of photons in there. The hotter it is, the more photons you can have per cubic meter. That's an important thing we're going to be getting to later because we're going to be talking about the cosmic microwave background density as well. This also leads us to the mean energy, the average energy, not the peak energy, but the average energy, which is about 2.7 times kT, which is the typical energy for at that temperature. Wow, that's a lot about black bodies. How can we put this to some use? Well, if they have a temperature of 310 Kelvin, which is roughly you, if you're not sick or anything, then the average energy that's coming off of you is about 7/100ths of an electron volt. And that leads to a wavelength of about 1.7 times 10 to the minus fifth meters, which is about 17,000 nanometers. So you radiate in the mid-infrared. You're an infrared radiator. And so then when somebody comes up to you and says, oh, you're warm, that's because you're radiating a lot of mid-infrared photons. Now compare that to the sun. The surface of the sun is 5,800 Kelvin. Now the average solar photospheric photon is about 1.3 electron volts, which has a wavelength of approximately 900 nanometers, and that's in the near infrared. Wait a second, we can see the sun. When we can't see infrared light, we see the sun with visible light. But the blackbody distribution curve guarantees that a lot of photons are present right next to the peak. Visible light is between 400 and 700 nanometers, and the sun has a huge amount of output right between 400 and 700 nanometers. Visible light lets you see, and the peak wavelengths keep you warm on a summer's day. Now, cosmologically, we expect the universe to be suffused with huge numbers of photons, not just from stars, but from nucleosynthesis processes in the Big Bang at the start of the universe. So photons in a blackbody are going to be really important in this lecture series. Lastly, we come in our discussion to dark matter. So dark matter is a really interesting thing and a subset of all of the materials that we're going to be talking about. It's one of the greatest mysteries. There's really no mysteries about protons and electrons and neutrons. Except neutrinos have some mysteries with the masses. And there's really not a lot of mysteries with photons. But comparatively speaking to these others, dark matter is a complete mystery. And what is it? So there's two basic definitions, and astronomers traditionally have called it there's mass there, but it's simply too dim to see. And that's its original definition. The term dark matter came from German, which was dunkle Materie, which was coined by Fritz Zwicky in his studies about the nature of the Milky Way. Now, particle physics and astrophysics will say that dark matter is anything that has mass that doesn't interact with photons in any way. It doesn't scatter light, it doesn't emit light, it doesn't absorb light, it doesn't create photons or anything. So why do we think that dark matter exists in the first place? Well, first, the Milky Way shows in its galactic rotation curves that it's not Keplerian motion in the outer areas. The rotation curves for almost every single spiral galaxy, in fact, all spiral galaxies, don't drop off the way they should if the center of the galaxy was where all the mass was concentrated. They have flat rotation curves out to their however far they can see, which means there's more mass there than is expected. So basically, they're rotating too fast at the outer reaches for the material that is visible to light. Next, massive elliptical galaxies have velocity dispersions of their stars that are too fast for the galaxy to stay confined. And next, similarly, galaxy cluster dynamics shows that individual galaxies inside of big clusters of galaxies tend to be moving too fast for the galaxy cluster to stay gravitationally bound. Gravitational lensing of background galaxies by foreground galaxy clusters also shows this because the only way to map the appearance of the background galaxies is to posit additional mass due to dark matter that exists inside of the galaxy cluster. Also, cosmic microwave anisotropies require that about 5/6 of the matter energy density be cold dark matter. That is, well, it's some sort of dark matter that behaves like matter, but is not the type of thing that's made up of protons and neutrons and so forth. Also, structure formation in the early universe. In the early universe, it was radiation dominated. And that would mean that the normal matter would interact with that light and be carried along by the photons that are incredibly intense. But since dark matter doesn't do light, it therefore can make clumps because mass works, right? Gravity works on mass. So it can make clumps, and then that would be the seeds of later galaxy clusters and structure that would be formed into superclusters of galaxies and so forth. Without this dark matter, there would be no clumping, and galaxy structure formation would happen far later than is seen. Now, technically, neutrinos do qualify as dark matter because they have mass, but the power spectrum of the cosmic microwave anisotropy measurements by the COBE, WMAP, and Planck require that hot dark matter, meaning dark matter that is moving close to the speed of light or relativistic, be in a really short supply. Basically, the existence of a lot of relativistic dark matter would also suppress structure formation in the early universe, making galaxy formation happen later. But Recent JWST observations seem to be supporting an earlier and faster than expected galaxy formation, which means that you really do need dark matter in the early universe to create those seeds in order to make galaxy formation and galaxy structures. So what exactly is dark matter? Well, dark matter is kind of a weird thing. Let's just pretend for a while that it's like planets or burnt out stars or whatever, like huge amounts of gas and dust that are out there in the universe, made up of just protons and neutrons and other things. Maybe it's more hydrogen, maybe it's more helium, but that's baryonic dark matter. And there's a lot of lines of evidence that suggest that the majority of dark matter isn't baryonic. First, if there was gas or dust, then it would be, if there's enough of it to make the amount that needs to be seen, then that needs to be seen by the kinematics of things that we see, these velocity dispersions, rotation curves, and everything else we've seen, then it would be visible because it would come to the same temperature as the background stars. And this is similar to the Olbers paradox argument. You have enough stuff in the way, it's going to absorb the light and it'll get warmed up so you can see it. Next, Big Bang nucleosynthesis predicts the observed abundance of chemical elements. But if there's more baryons, then there will be also more helium and lithium and heavier elements synthesized during the Big Bang. So agreement with the observed abundances requires that baryonic matter only makes up about 4 or 5% of the universe's critical density, because we do think that the universe is a flat universe as a result of WMAP and COBE and the Planck probe, as well as many other things. So if that's the case, in large-scale structure observations and other observations indicate that the total matter density, including from this all, is about 30% of the critical density. So 30% of the critical density, which we think is actually the density of the universe, is actually in the form of some sort of cold dark matter. 5 parts dark matter, cold dark matter that's non-baryonic, and 1 part normal matter. Next, astronomical searches for gravitational microlensing in the Milky Way found only a small fraction of the dark matter maybe in the dark, compact, conventional things. And those things have this wonderful contact name of MACHOs, massive, compact, halo objects. These things, if we excluded, I mean, these searches have said, well, there's stuff out there, obviously, because, there will be black holes and there will be rogue planets, and those are interesting in their own regard. But there's not enough of them. And the excluded range of object masses goes from about half the Earth's mass up to about 30 solar masses, which would be some big, big, big black holes. And that covers almost everything that could contribute as machos. Finally, the WMAP and Planck probes indicate that, as I said, 5 out of 6 parts of the total matter is in a form that only gravitational effects. So that leaves us with non-baryonic dark matter. And there are 2 real main candidates for non-baryonic dark matter. One is hypothetical particles like axions, sterile neutrinos, WIMPs, weakly interacting massive particles, supersymmetric particles from the beyond the standard model of particle physics, atomic dark matter, or geons, which are black holes made of light. Kind of a weird thought. Or fundamentally, just simply primordial black holes. That's the other one. So basically, once a black hole ingests any kind of matter, baryonic or not, the distinction is lost. So you have no idea. So primordial black holes could be the fundamental non-baryonic dark matter with all the other stuff floating around. Non-baryonic particles don't contribute to the formation of elements in the early universe. So they don't have any part of it. And so Big Bang nucleosynthesis is not affected by them. And so they would only find their presence through gravitational effects or weak lensing of background galaxies. But here's the thing. Dark matter, what it is still an incredibly wide open question. We know it exists, but we have no idea what it is. Okay, that rounds out kind of what we have for our particles in the universe, and we really kind of can break it back down with all that discussion to these 6 things. There's protons, there's neutrons, there's electrons, there's a bunch of neutrinos everywhere, there's a scad more photons than you can possibly imagine, and dark matter. A lot of it's there. We have no idea what it is. We don't know what it's made out of, but we know it's there. So these are our particles, and these are the typical particles that we will find in cosmology and that we're going to be using for the rest of the course. At this point, I'd like to say thanks to my Patreon supporters. They've been great for helping me along with all these kind of things, providing suggestions and so forth. And if you'd like to be a Patreon supporter too, please check the website out and subscribe. In any event, please like this video, subscribe to the channel, share it everywhere on social media, let everybody know that there's cosmology happening over here on Kendall's channel. It'd be great to have you do that. And next time, we'll go through the final section of this chapter 2 for Ryden's textbook, which will be on the cosmic microwave background. See you soon.